Hello, my name is Tim Frederick, and I'm with EPA's Region 4 office that's located in Atlanta, Georgia, in the southeastern United States. There I work in our Superfund program, which is our program for dealing with hazardous waste sites. I'm very excited to have this opportunity to talk with you, and I look forward to sharing our experiences with you. Today I'm going to be talking about an overview of high-resolution site characterization, on-site soil sampling, and analysis methods. I'm going to be talking about how we collect those soil samples in the field, the analysis of samples, and as importantly, the field processing that may need to be done to make sure that you get quality results. Talk a little bit about how we evaluate the data to make sure that it meets our data quality objectives, and I'll end with a few short case studies kind of illustrating some of those points. So let's begin by talking about how we collect soil samples. This table presents an overview of traditional sampling methods, discrete or grab sampling, composite samples, and incremental samples. I'll go more into each of these types of samples and which ones may or may not be suitable for high-resolution site characterization. When we're talking about what type of sampling that we should do at a site to best characterize a site, our data quality objectives are key. We need to understand upfront what the purpose of the sampling effort is. We should carefully consider how the data will be used to inform decisions. Are we just wanting to know if contamination is present or not? Do we want to fully delineate the nature and extent of the contaminants in the soil? Are we collecting data to inform risk assessments? Are we collecting the data to confirm that our removal has been fully completed and meets our cleanup objectives? We might want to do different things for each phase or each type of sampling. HRC sampling seeks to address the scale of the sampling. What's the size of the area that we need to sample or reach some sort of decision about? We need to think about sample spacing and density. For high resolution sampling efforts, we generally want to have our sample spacing reduced and have high density sampling. And those two things can help to inform where those samples should be collected. It helps to take a moment and think about our goal of soil sampling. The goal of most soil sampling efforts is to collect a sample or samples that are representative of the area that we want the data to inform. If the data are not representative, it can lead to bad decisions. We want to make sure that the soil that goes to the lab adequately represents the area that we're sampling. Soil is a problematic medium because of its inherent heterogeneity. In soil, heterogeneity is the rule. The picture on the far left shows the number of possible samples that could be collected within a single square foot area if we're using a 2-inch sampling tool. It's about 36. The next figure to the right shows the variability of samples that were collected for uranium within a single square foot sample area. The data vary widely, and as a result, they could lead to differences in decisions based solely on chance related to the sample location. Similarly, the figure on the right shows data collected at a 1-foot interval on a transect for arsenic. Again, these data vary widely and could also lead to differences in decision making depending on the sample location selected if we were only selecting one of these sample locations. Overcoming this heterogeneity can be a challenge and is the goal of HRSC soil sampling efforts. One of the reasons for soil heterogeneity is the variability of soil particle size within any given sample and which fractions are selected, intentionally or not, for analysis. In the photo above, an unprocessed soil sample was passed through a variety of sieves in the field. The resulting size distributions can be seen in the picture. We could see that we have very coarse soil particles ranging all the way on the right, all the way down to very fine soil particles on the left. Taken together, these samples would create a sample that have a great deal of heterogeneity just in composition. Discrete samples can be collected from biased or from random sample locations. A discrete sample is collected from a single location. The sample volume and additional sampling processing can vary accordingly. Discrete samples are easy to collect and may be useful for collecting information about a specific area of interest, such as a visible release. Discrete sampling methods do not typically address the potential heterogeneity of the soil. High density of discrete samples could be collected for HRC applications to determine the potential distribution of contaminants across an area of interest. However, we would still expect the between sample concentrations to be highly variable. A typical composite sample is assembled from a small number, like 5, discrete samples that are combined in the field. The component discrete samples are typically collected in a quincunx pattern or a die pattern, as is shown here, that may or may not be of equivalent size or mass. The samples are typically mixed in the field and placed in the sample containers specified by the analytical method. The sample volume and additional sampling processing can vary. This method is not very rigorous typically and is not usually used in HRSC soil sampling applications. Incremental samples, also called incremental composite or multi-increment, are structured samples that provide an unbiased, reproducible estimate of the mean of a given volume of soil, what we typically call a decision unit. An incremental sample is assembled from a large number of small samples, 30 to 100, of equivalent size or mass that we call increments. They're collected from random or systematic random locations across the decision unit. The process typically yields a large sample mass, greater than a kilogram in most cases. Additional sampling processing in the field or laboratory and subsampling is usually required. Incremental samples are collected with specialized sampling and subsampling tools that are needed to properly sample and subsample the soils. I'd like to spend some time talking about the ISM method because it's designed to address the inherent variability in soil data and is often used in HRSC sampling applications. This figure provides some additional detail on how incremental samples are constructed from multiple increments. We can see that there are circles, X's, and triangles across here that are representing individual increment locations. So if we begin with the circles here and collect an increment here, each place that we see a circle, and move through the sampling area, systematically collecting each of those, an increment at each of these O locations, we see that they come over here and are used to construct a sample. Similarly, all of the X's moving through space are collecting increments moving systematically through the sampling area, and likewise, the triangles, we can move through each of the triangle locations and construct a third sample. So although there are many increments that are collected to construct these samples, we end up with 3 samples that are analyzed. These are called replicate samples because we're replicating the process of sampling systematically and rigorously the area that we're sampling, called the decision unit. The systematic, rigorous process is designed to minimize sampling and analytical error. So we're going to get data that are reproducible, and we can evaluate these replicate samples to see how reproducible they are. We can quantify the variability between these samples to let us know how much heterogeneity is in the soils that we're sampling from. This is a figure from a paper that I wrote with some others about incremental sampling, where we were for a research project, and it demonstrates how the incremental sample can be constructed. So here we have a 1/4 acre decision unit. A decision unit is the area that we want to make some decision on. Each of these grids is sampled. You can see that here I used a circle, a triangle, and a square to represent the 3 increment locations. These locations within each grid were selected randomly. We used a random number generator to come up with these coordinates, which we were able to measure off to make sure that we're being systematic as we moved from each grid. So in each grid, a increment would be collected, a same-sized increment would be collected from each of the locations where the circle is all the way through to carefully construct our 30 increment sample, similarly with the triangle and again with the square. So we would have 3 samples at the end. Incremental samples are typically collected with 30 to 100 same-sized increments collected to build 1 incremental sample within a decision unit. The number of increments is typically based on the expected variability, not the decision unit size. So if we went from this 1/4 acre to a full acre, we could use the same number of increments if we suspected that the variability would be similar in the larger DU. Sampling design should be site-specific and based on data quality objectives and systematic planning, like any other sampling process. Let's talk briefly about some of the differences between discrete and incremental sampling designs. The figure on the left represents a 1/4 acre to be sampled that has been gridded, and 3 randomly selected samples, shown here as red triangles, have been collected to represent the sampled area. This could be a typical non-HRSC sampling approach. The results are likely to be highly variable. The figure on the right shows how 2 incremental replicates are being constructed across the same sample area. This high density of the increments, in this case 100 increments, demonstrates how the ISM samples, which involve same-size increments, are able to better represent the unbiased mean concentration across the sample area than the limited number of discrete samples shown on the left. If a more detailed understanding of the distribution of the contaminants, the nature and extent of the contaminants across the space is needed, an alternative to ISM might be to collect high-density discrete samples, for example, collecting all of the triangles in the figure on the left and analyzing those samples using an HRSC analytical method such as XRF. The variability of the high-density discrete samples is still likely to be higher than the variability between the replicate ISM samples, but they provide that additional information about distribution. A key component of incremental sampling is collecting same-sized increments throughout the decision unit. This is done so that each increment represents proportionally the overall concentration of the incremental sample being collected. Using a specifically designed sample tool facilitates the collection of same-size increments. It helps to make sure that as you move from increment sampling location to location, that a same-sized increment is collected in each location. The increment mass or volume that is collected is a function of the sampling depth in the sampling tool diameter. It's important to always pilot a variety of sampling tools at your site prior to mobilization to make sure that the tool that you've selected to collect your increments is best suited to the site conditions at your location. These photographs show a variety of sampling tools that can be used to collect same-size increments for surface soil sampling applications. The tools can vary by width, depth, and release of the soil contained within the sampler. The third picture from the left shows a simple hand trowel and stainless steel scoop. This was used at a site after it was found that the soil was too sandy to stay inside of the original sampling tools that were selected for the project. The sample simply was released from the tool as soon as it was pulled from the soil, and we were unable to collect any sample increments. By using the hand trowel and the scoop, we were able to make sure that we had same size increments throughout the sampling area. Clay soils and damp soils can also present challenges depending on the type of sample device that's also used. For this reason, again, it's recommended that a pilot test should be conducted ahead of full-scale sampling at a site, if possible, to ensure that the sample tool is appropriate for site conditions. An important part of developing an incremental sampling strategy is determining the proper number of increments to collect. This decision, as I mentioned earlier, should be based on potential heterogeneity, not decision unit size. As the expected variability increases, the number of increments should also increase. Now, in order to have an understanding of the variability, you may need to collect some screening level data at a site to see what the variability between samples looks like. You may have some other existing data, but you should have some idea of how heterogeneous you expect the soil to be in a given sample area. Typically, 30 increments is a minimum recommendation. 30 to 100 increments, depending on variability, can be collected. The state of Hawaii recommends a minimum of 200 increments when sampling for PCBs, because for a number of reasons, PCB contamination in soil can be highly variable from location to location. And to overcome this heterogeneity, we can increase the number of increments even more, up to 200. So EPA method 8330B says that the error associated with distributional heterogeneity, the way that the contaminant is distributed throughout your sampling area, is inversely related to the number of individual increments used to build the sample. So again, as your number of increments goes up, the sample error that's associated with your distributional heterogeneity is going to go down. So when in doubt, a simple rule of thumb is to collect more increments. Another key component of incremental sampling is collecting replicate samples. Replicate samples, as the name suggests, replicate the number of increments. These use the same sampling tools. They're collected in the same manner, as many replicates as are collected in a decision unit, in order to evaluate the sample variability. We can use this quantified measure of variability to evaluate the precision of these samples. And we can use that information to determine whether our sampling strategy adequately addresses sampling error and heterogeneity that are always going to be integral to sampling in soil. So how many replicates do we collect? Generally, a minimum of 3 replicates are recommended. This photograph shows a sample project where we collected 5 100 increment surface soil samples. We collected 5 because we were collecting some highly variable soil. We were looking for asbestos in soil, which can have a high degree of variability. And so we wanted to increase our replicates to have a better measure of the variability, to see how we were doing, to see if 100 increments was truly enough to overcome that inherent heterogeneity. Again, more or fewer can be collected depending on your site-specific data quality objectives. So let's take a moment to talk about some definitions. Incremental samples are collected within decision units. I've used this term in a few slides without defining it, so let's do it now. A decision unit is the smallest volume of soil for which a decision is going to be made based on ISM sampling. A decision unit could be as small as a residential yard, or it could be many acres. A related concept is a sampling unit, which is a volume of soil from which increments are collected to determine an estimate of the mean concentration for that volume. A decision unit and a sampling unit are often the same, but they can be different, and I'll show you an example in a moment. The selection of a decision unit should be carefully considered. It should be based on what we know about site operations. It should be based on what we know about potential data concentrations from either screening efforts or from existing data, but they should be carefully considered to make sure that we're sampling in a way that minimizes heterogeneity that might be unrelated to the contaminant concentrations that are present. Decision units can be the same or different from an exposure unit. An exposure unit is a term that we use in risk assessment that defines where exposure might take place. So an example that I gave earlier of a residential yard, that might be the decision unit of interest, but it's also where exposure for a child may take place within his yard. So that could be an example of where our decision unit and our exposure unit are the same. Sometimes a distinction is made between a decision unit and a sample unit. Usually, these are the same as indicated in the top figure. The decision unit, the area for which a decision is being made, is the same area that is being sampled. In the bottom figure, a decision is being made in the same area, but smaller areas, sampling units, are being sampled to provide additional information. This is distinct from an area with multiple decision units, which are being sampled separately and for which decisions will be made separately. Decision units can extend vertically depending on our conceptual site model of where we expect contamination to be present. This figure is simplified for readability, but the main idea is that a sample core can be collected and used to understand the average concentrations in different depth intervals that can be designated as separate decision units. A minimum of 30 increments is still recommended. So if we look at one of these cores, this one that is circled in yellow, we see that there have been 30 such borings installed throughout our decision units. The sample interval from this one core, we can collect an increment from the 0.5 to 1.5 sample interval and have that contribute to a sample that will represent decision unit 1. We can then go from the 1.5 to 3 foot interval and collect a separate increment from the same core that can contribute up to, as one of 30 other increments that will be used to represent decision unit 2. We can go back to the same core from the 3 to 5 foot range, collect another increment that will be one of 30 such increments that are used to understand the average concentration throughout DU3, and then we can extend from the 5 to 10 foot increment, interval, to collect another single increment that will be one of 30 such increments that are combined to construct a sample to represent DU4. Again, decision units are that smallest area that we need to make a decision on, and we can construct them in a variety of ways. The picture shows a release area that we may need to make a decision on. Does the concentration within the spill area exceed some regulatory criteria that would necessitate taking an action on the part of our agency? So we can draw our decision unit to represent that area that we can see has been visibly impacted by our spill area to help us make that decision. Decision units can be equivalent to exposure areas. For example, this is a residential yard. We know that children play in this yard. That's where they may be exposed to contaminated soil. So we may want to sample that as a decision unit on which we need to make some decision. Do we need to take action here or not? Decision units can also be constructed or established based on existing data. In this case, we knew that a soil pile, shown as the box with an X here, contained high concentrations of lead that was from reclaimed waste from shooting ranges. The topography sloped in the direction of the arrow, and corresponded to areas of higher lead concentrations from existing samples. The darker circles here are representing higher concentrations of lead in the soil. DU1 was created to establish a decision unit that captured the main area of potential contamination based on topography and our existing data. DU2 and DU3 and DU4 were created based on topography principally. Later, we added DU1A to see if heterogeneity in the field samples in DU1 replicates were the result of potentially lower concentrations in that area. So that was a decision unit that was subdivided for the larger decision unit 1 later, after we had some additional data in hand. When little is known about the potential concentrations or former operations at a site, field screening tools may be useful in determining appropriate decision units. In this example, an XRF is being used to collect in situ readings for arsenic to see if areas of higher or lower concentrations could be quickly identified, and decision units could be developed accordingly and could be sampled by more rigorous sampling procedures. We typically don't recommend using in situ XRF measurements for decision making, but they can help us figure out how we may want to sample a given area and divide it into decision units. Let's look at a few examples of incremental sampling in the field. When collecting incremental samples in the field, it helps to have a clear idea of where the decision unit is, what its boundaries are, how it will be divided to collect increments, where the increments are going to be collected from, etc. In this picture, which was part of a research sampling effort in Washington State, the team wanted to be very clear for documentation purposes. A physical sample grid was laid on the ground using rope. You can see the grid laid out here. Each increment location, which was again selected by using a random number generator that I showed you earlier, to pick coordinates that were applied to each grid square to construct the sample. Each of those increments was identified by a survey marker flag. You can see one here. This level of advanced preparation is not always necessary or possible, but it can help to make things very clear about how the samples are going to be collected. This picture shows a second DU at the same site as the previous slide. You can see that the sample grid is laid out with ropes in the foreground. Higher grass in this area made it much harder to lay out that grid and to place the survey markers for each increment location. However, it was helpful in this case to have everything laid out clearly before sampling, because the sampling team were in PPE, which limited the team's vision and movement. The team is sampling soil contaminated with asbestos that required the use of respirators and other protective equipment. So having the grid laid out and the sample locations really helped the team to know where they needed to go next to collect each of the increments to build the samples. But laying out a sample grid physically in space is a luxury that cannot be afforded at some locations. At some sites, it is just not going to be possible or practical to lay out a sample grid or place the markers for increment locations. In these cases, alternative methods will be needed to keep track of the team's location within the DU and the approximate location of each sample grid and each increment location. In this case, flagged wooden stakes were used to mark the corners of the decision units. The location of the next sample was paced off as the sampler made his way through the brush. GPS was of limited value due to the dense vegetation. Things could be measured off with a tape, etc., but things were difficult. For the location in the previous slide, a laminated sample sheet was used to keep track of the samples collected and ensure that all the increments were collected for each sample. These samples were 100 increment triplicate samples that were collected at the site in this decision unit. Because of the ground clearing required to access each location, this was an effective way for the team to ensure that they didn't lose track of where they were between sample locations. You can see from the dates laid out here that it took quite some time for the team to move through this DU and collect all of the increments needed. So it was critical to have a method of keeping track of where they had been, where they had not been, and which samples needed to be collected. Another advantage of incremental sampling techniques is that the samplers become very familiar with the soil conditions throughout the site. In the photograph above, a coworker and I are collecting 5 100 increment replicate samples within a quarter-acre decision unit in Oregon. At the end of the sampling, we had collected 500 total increments in our decision unit. We quickly learned that although the area seemed to be homogeneous before we started sampling, that it varied in distinct patterns across the site. Some specific areas were sandier than others, some had a more clay-type soil. This type of familiarity with the site could become useful in understanding the fate and transport of contaminants across the area, or could explain unexpected heterogeneity between the samples. But you would otherwise not have this intimate knowledge with the soil in your area if you were not collecting such high density increments throughout the decision unit. Individual increments can be collected with specialized hand tools. In the picture on the left, an incremental sampling tool is equipped with a slide hammer that can be used to help drive the tool to the necessary depth in harder soils. In the picture on the right, a direct push technology or DPT rig is being used to hydraulically drive the sample core to the desired subsurface depth, in this case 12 feet below land surface. The collection of incremental samples can vary considerably in the amount of time collected. On another slide that had dense brush, heavily wooded area, it took a couple of days to collect the increments across that site, across that decision unit. In this yard, a small residential yard, one 30-point composite was collected in about 8 minutes. In the handout version of this presentation, there's a video that I'm not able to show you now and narrate that shows how the sampling team was collecting these samples. But under ideal conditions, a sample team can quickly construct a sample with the desired number of increments. In this case, 2 people are using incremental sampling tools to methodically collect 30 increments across a residential yard. A third team member is collecting the increments in a foil pan. Note that a grid has not been physically placed on the ground surface. The experienced sample team has sampled many yards, and they are able to approximate evenly spaced increments across the yard. For this project, the team has sampled over 1,000 residential yards and have become very efficient at collecting samples quickly and correctly. However, as noted in those previous samples, adverse site conditions can slow down that effort considerably. Regardless of sampling method, our sampling strategy should be based upon a conceptual site model, an initial conceptual site model that lays out our understanding of release mechanisms, potential fate and transport, potential exposure areas, and confirming our conceptual site model through our sampling strategy. The level of sampling needed to do all of that will depend on our data quality objectives, which can in turn be informed by existing site data. I'd like to take a moment to introduce you to a website that might be useful to you to help design sampling and analysis strategies for your sites. The U.S. Federal Remediation Technologies Roundtable website, and I have a link at the bottom of the slide, is a good reference that provides very detailed information on methods that are available to access sample locations and available HRSC analytical methods by sampling media and by contaminant classes of interest. I'll discuss some of these sample access and collection methods for soil in the next few slides. So one way to access sample location areas is by drilling. And access here is used to describe the method to get to the soil interval of interest for direct in situ measurements or to obtain a sample for ex situ measurement using HRSC methodologies or to be sent off to a lab. Drilling methods can vary depending on whether the subsurface conditions are consolidated or unconsolidated. They can vary by impact on the substrate that's being drilled through. These methods will be discussed in more detail in the groundwater tools section. Another method for accessing soils for analysis is using drive methods such as cone penetrometers or direct push samplers. Pictured here is a direct push technology rig that is used to collect soil at depth. Typically for ex situ analysis, it'll withdraw a core of soil that can be analyzed in the field or collect a sample that can be sent off to a fixed laboratory. And we've also talked about access tools that are handheld, things like scoops, spoons, shovels, hand augers, tubes that can be driven or pushed into the soil using hand pressure. These are usually used for collecting surface soil samples, and we've shown some of these in our discussion of incremental sampling tools. I'm going to be talking about how we collect those soil samples in the field, the analysis of samples, and as importantly, the field processing that may need to be done to make sure that you get quality results. Talk a little bit about how we evaluate the data to make sure that it meets our data quality objectives, and I'll end with a few short case studies kind of illustrating some of those points. Now let's talk about analysis of samples in the field and field processing that may be necessary to improve on our analytical results of those samples. Selecting tools for analysis can be dependent on a number of factors. It depends on the contaminants. We may need to do different things for volatile organic contaminants than we would do for metals, for example. It depends on the sample access methods, how we get to the sample interval of soil of interest. It can depend on whether in situ or ex situ analysis is preferred and whether the ex situ analysis is in the field or in a fixed laboratory offsite. And critically, it can depend on the data quality objectives, the accuracy and precision that are needed for our decision making or our other sample collection purposes in the field. Some sample analysis tools for VOCs, SVOCs, and pesticides can be broken up into in situ or ex situ sample tools. In situ is typically limited for soil for laser-induced fluorescence techniques. Ex situ, however, we can use PIDs, FIDs, gas chromatography, detector tubes. Again, this can be dependent on our data quality objectives and the decisions that need to be made at the site. Sample analysis tools for metals. We have the very common X-ray fluorescence or XRF tool that can be used to collect real-time measurements ex situ in the field, or in situ if we just want to collect measurements of the surface in place. Increasing in complexity, atomic absorption spectrometry or inductively coupled plasma atomic emission spectroscopy tools can be used in a field lab setup where we can collect these measurements directly in the field without sending to an off-site fixed lab. But we'll need to do some extraction of the soil for analysis. We can use less sophisticated colorimetric kits, and there are some others. Sample Sample analysis tools for radionuclides can vary depending on the type of radiation, whether it's alpha, beta, or gamma. Gamma can be detected from quite a distance away. Alpha and beta radiation will need to be closer to. But we can use common handheld radiation detectors for screening samples. For alpha and beta, it's not recommended for gamma, which has more energy, requires more personal protection. We can use a gamma ray spectrometry. We can use nuclear magnetic resonance, and there are others that can be used in the field as well. And there are some tools that we can set up to analyze in the field for explosives. We can have a field gas chromatography lab set up, a mass spectrometry lab set up in the field. We can do GCMS. We can do ion mobility spectrometry, and some others. Perhaps an underappreciated part of doing field sampling and analysis is the sample processing that can help to improve the reliability of the analysis of that sample. We should always remember that what happens to your sample in the field or in the field lab is as important as what you did in the field to collect it. If you have used very rigorous means to collect a sample, your sample processing should be equally as rigorous. Field laboratory processing and subsampling should also be conducted appropriately to reduce the heterogeneity within the collected samples and to improve the overall data quality. Verification procedures may be required to confirm that the data quality objectives are met. Some form of ex situ sample processing may be required to ensure that high-quality, reproducible data are obtained from the sample collection effort. Some typical soil processing steps include drying, grinding, sieving, and subsampling. The sample processing steps needed will depend on the contaminant as well as the analytical methods selected and the data quality objectives. Drying samples may be required to ensure that soil moisture is not interfering with the field analytical tools or to facilitate sieving of samples. For example, soil moisture should be less than 20% for XRF analysis. In the picture on the left, electric warming ovens are being used to dry samples at 200 degrees Fahrenheit in a field trailer prior to being analyzed. In the southeastern United States, where I work, temperatures can be very high in certain months of the year. In the picture on the right, collected samples are being air dried in the field on a sunny 94-degree day. Moisture readings can be collected using a moisture probe and recorded to document that the target moisture goal was achieved in the field. Sample grinding may be a sample processing step that can be performed in the field if a goal is to reduce soil particle size heterogeneity. Breaking up soil clumps can also facilitate sieving. In the lab, this is done with tools such as a puck mill. In the field, that type of tool would be impractical due to decontamination concerns. However, soil clumps can be disaggregated by hand pressure using a stainless steel spoon to reduce the size of large soil particles. For some contaminants, such as metals, the fine particles are of interest. Sieving soil samples to separate the fine particle sizes for analysis can be performed in the field. Using stainless steel sieves in the field can be difficult due to the time needed to decontaminate and dry the sieves before reuse. On a recent project where thousands of samples were collected and sieved, the project team solved this problem by using disposable sieve mesh, pictured here, that are placed between easily cleaned reusable sieve collars. This greatly improved the overall efficiency of the sample processing and reduced the sample heterogeneity and resulted in very good correlation between field and lab analysis results. Incremental sampling methods can produce very large samples on the order of 1 to 5 kilograms depending upon the number and size of increments. Accordingly, it's often necessary to reduce the sample volume for analysis by using subsampling techniques. In the photograph on the right, a 2-gram subsample of fine soil particles has been systematically subsampled from the larger 2-kilogram sample on the left that was collected. It's important when subsampling to maintain the representativeness of the sample all the way through to analysis to get the best sample results. To do this, subsampling techniques should be as rigorous as the sampling method itself. EPA has published a document called Guidance for Obtaining Representative Laboratory Analytical Subsamples from Particulate Laboratory Samples, and the link is provided for you here. The subsampling guidance document ranks the subsampling methods from best, which is a sectorial splitter, to the worst, a simple grab sample collected from your original sample. This table can be used to evaluate subsampling possibilities in the field if needed. Many of these subsampling methods can be easily implemented in the field, others are more difficult, but a variety of potential methods is presented here. In this example, the incremental soil sample that was collected on the left has been spread out on a stainless steel tray and then has been systematically subsampled by building an incremental sample of the desired volume for analysis. This method is ranked number 3 in the subsampling method rankings of the referenced guidance document. The photograph on the left shows a riffle splitter, which was ranked in number 4, being used in the field to reduce subsample size. On the right, a cardboard box lined with aluminum foil has been used to create a 90-degree angle along which a sample can be spread into a 2-dimensional slab cake that can then be subsampled by alternate shoveling, which was ranked number 5. Each of these methods and the method on the previous slide provides a systematic method of collecting a subsample that is representative of the larger sample that is then ready for ex situ analysis based on the selected tool in the field. I'm going to be talking about how we collect those soil samples in the field, the analysis of samples, and as importantly, the field processing that may need to be done to make sure that you get quality results. Talk a little bit about how we evaluate the data to make sure that it meets our data quality objectives, and I'll end with a few short case studies kind of illustrating some of those points. Now let's discuss how we evaluate the data that's been collected using these tools as part of our dynamic work strategy to make sure that we're evaluating data in real time and making the necessary adjustments to our overall strategy as needed. Proper data management and analysis is critical to any successful HRSC sampling effort. HRSC often generates very large data sets which require a pre-designed strategy for effective management, analysis, and communications. For field efforts using a dynamic work strategy data collection approach, newly collected data are ideally processed in real time. Following data quality assessment, the data are stored electronically and then evaluated spatially to refine the conceptual site model and to support the dynamic selection of additional sampling locations. Data must be collected at sufficient density to ensure comprehensive analysis of data trends at the scale of resolution appropriate to address site heterogeneities. Data may be collected in multiple formats, whether it's electronic, handwritten logs, etc., and all of that data has to be maintained to ensure that data integrity is maintained throughout. All data should be geolocated as possible, and we must evaluate the data in as close to real time as possible to determine if modifications are necessary to our dynamic work strategy. Depending upon the data quality objectives of the sampling effort, a key measure of the effectiveness of field analysis methods may be to establish a correlation between the field measurement data and data obtained from a fixed laboratory for the same samples. paired data can be quickly evaluated by a regression analysis to determine the strength of the association between the data. In this example, 50 samples of paired data have been evaluated. The regression analysis shows a correlation with an R-squared of 0.98. That's near perfect analysis and is about as good as we're going to get with environmental data. Another thing that we can do to evaluate our data is to collect multiple readings of the same sample. When using field methods such as an XRF, colorimetric methods, collecting multiple readings of the same sample allows us to measure and quantify within sample variability using the method of analysis that we've selected. We can determine whether within sample has been adequately controlled by our sampling and analysis methods, and we can make changes as needed in real time using our dynamic work strategy to seek other methods of data collection if needed, depending on our data quality objectives. When collecting incremental samples, we typically do this in triplicate so that between sample variance can be quantified. This is a measure of whether the samples are producing a reproducible estimate of the mean concentration in the decision unit and whether the sample collection processing and analytical methods adequately control for heterogeneity. The relative standard deviation, or the coefficient of variation, is calculated as a measure of variance. Relative standard deviation is a quantification tool that evaluates precision but not accuracy. So we have to think about what an unacceptable RSD might mean for the project. A low relative standard deviation generally means that our heterogeneity in our soil has been adequately controlled through sampling and analysis, and that we can rely on the data, that the data are reproducible. High relative standard deviation may indicate that our data are not very precise, that there's some underlying heterogeneity, which may tell us all that we need to know. However, if we're looking for reproducible estimates of the mean concentration, we may need to consider areas where error may have been introduced either in the sampling or in the analysis of our samples so that we can adjust our dynamic work strategy to get more precise data. Some potential sources of error are listed here that we can consider for why we may have very high variability within our samples. It could be anything from the number of increments to the DU size and shape that we selected, or it could be that our field processing or lab processing was inadequate, that we have subsampled improperly, that our extraction or digestion methods introduced some error, or that our analysis was the source of the error. I'm going to be talking about how we collect those soil samples in the field, the analysis of samples, and as importantly, the field processing that may need to be done to make sure that you get quality results. Talk a little bit about how we evaluate the data to make sure that it meets our data quality objectives, and I'll end with a few short case studies kind of illustrating some of those points. Let's look at two short case studies that highlight some of the things that we've been talking about today. At this site, low-density sampling collected through traditional means and sent to a lab for analysis was extrapolated to produce the concentration gradients below. The concentration gradients that are orange and red are the highest concentrations. The contaminant of interest, PCBs, has both relatively high analytical costs and, if determined to meet the regulatory designation of hazardous waste determined by its concentration, it can have disposal costs up to 300% higher than the soil contaminated with lower concentrations. An HRSC approach was used to collect high-density samples that could be generated in the field and used to refine the soil disposal disposition. Samples were collected at 20-foot by 20-foot grid at several depths to determine the nature and extent of contamination. Vertical samples were collected at 6-inch intervals. A dynamic work strategy was used to determine the horizontal and vertical extent of samples that needed to be analyzed in the field. Samples were analyzed in the field using a commercial electrochemical field analysis method. Correlation of the field samples with lab samples demonstrated that the results met the data quality objectives. Sample results using the HRSC sample and analysis methods were used to refine the estimates of the needed soil excavation. Excavation extent was confirmed with lab samples. At another site with PCB contaminated soils, incremental sampling techniques were used to develop a refined estimate for soil disposal. A test pit showed that soil beneath a parking lot slab was contaminated with visibly contaminated PCB containing oil. In this case, the site was divided into 11 sampling units. A decision was going to be made about the soil underneath the entire slab, but each sampling unit was going to provide additional information that would inform that overall decision for all of the soil. 30 increment samples were collected in each sample unit, and triplicates were collected from 2 of the sampling units. The sampled areas had increment locations marked with paint where each increment would be collected. A total of 450 total increments, or holes in the ground, were collected throughout this space. The skilled DPT operator on the site produced a core every 3 minutes. Of course, the paved area facilitated efficient sampling, but his ability was something to see. The handout version of this PowerPoint presentation includes a video that, again, I can't show and record over for today's purposes, but check that out if you can. He was producing these cores so quickly, and they needed to be processed by the field staff so quickly that they had to ask him to stop talking to them so that they could keep up with his talking. Measuring the depth of the visibly contaminated soil intervals that are marked with survey flags reading top and bottom allowed the team to develop a very precise estimate of the contaminated soil volumes that would need disposal. In the field, and it doesn't really show up as well in the photograph, there was a very distinct boundary that could be marked in each sample that showed that visibly contaminated area, and they were able to take a very precise measurement with 480 holes in the ground. They knew exactly how much of this material they would have that would require disposal. So these are the results in milligrams per kilogram of the PCBs, total PCBs, across the different sampling units. We can see that we have elevated concentrations throughout. These are all going to require some action. These were sent off to the lab for analysis, not for field analysis. But we were able to look at the triplicate samples and see how they performed. And using our calculation, understanding the mean and the standard deviation, we're able to calculate a relative standard deviation 12 and 26. Our RSD interpretation guide shows that's good precision. We're getting reproducible data that are high quality and we can make decisions with. So again, our incremental sampling data reduced some of the inherent heterogeneity. Our incremental sampling techniques reduced the inherent heterogeneity of PCBs and soils. Our high resolution of sampling allowed the project team to quantify very precisely how much of the soil needed disposal for estimation purposes. I'm going to be talking about how we collect those soil samples in the field, the analysis of samples, and as importantly, the field processing that may need to be done to make sure that you get quality results. Talk a little bit about how we evaluate the data to make sure that it meets our data quality objectives. And I'll end with a few short case studies kind of illustrating some of those points. And with that, we'll conclude our overview of HRSC tools and techniques for sampling soils. Thank you very much for this opportunity to speak with you today. And if you have any questions, we can answer some of those on the Q&A session coming up, or you can reach out to me via the contact information here. Thanks so much for your time.